Hello everyone. Today we are going to start our discussion on numeration systems whose bases are greater than 10. There are essentially two of them which are widely used. One is the base 12 system, the duodecimal, and the other one is the base 16 or the hexadecimal. Now, when we were discussing bases less than 10, I had mentioned that I will look at the ones greater than 10 separately in a separate video. And the reason for stalling this was that the numerals for base 12 and base 16 are a little bit unique, all right, different from those used in bases less than 10. All right, so we'll start with a discussion of how the numerals look in the base 12 system. Now, the logic of the numerals, how the pattern of the numerals are the same. They start from 0, all right? So the lowest value is a 0. It starts from 0 and goes up to 1 less than whatever the base is, all right? So if the base is 12, then it'll go up to 11. So starting from 0, the numerals for base 12 would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But after 9, we don't write 10, 11. We use the letters of the alphabet. So for 10 is denoted as A and 11 is denoted as B. So A represents, and let me use another color, A represents the number 10 and B represents the number 11, right? So you have to know that when working on problems. For hexadecimal numerals, base 16 numerals, it's the same thing except it will go all the way up to 15, correct? 1 less than 16. So the numerals would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, and F. So A has a value of 10, B a value of 11, 12, 13, 14, F has a value of 15. So that is how the numerals are for the base 12 and base 16. All right? So given that, if we were to convert from base 12 to base 10, again, the process is the same as converting from a lower base to base 10. The process will remain the same. You will be multiplying by each digit by its respective place values and then adding up all the values. However, we have to use the positional value based on base 12, based on 12, right? So let's look at how the positional values would look like. So it will be, the positional value for base 12 will be 12 to the power 0 for the extreme rightmost digit. Then it will be 12 to the power 1, 12 squared, 12 to the power 3, and so on. All right. So 12 to the power 0 will always be a value of 1, correct? 12 to the power 1 will be a 12. 12 squared would be 144. 12 times 12 is 144. And I made a mistake here. Let's correct this. It'll be 12 raised to the power 3, not 13. So 12 raised to the power 3. So 12 times 12 times 12 would be 1728. 1728. So these are the values for the place values, all right? So the rightmost digit has a value 1, then to the left it's 12, left to that is 144, and then 1728, 1728. So if we were to convert this value in duodecimal 39BA, let's work on the process. I'm going to first spread out the digits. So I'm going to write it as 39BA. So I can show the steps clearly. So A represents the number 10. All right. To remind yourself, you may just want to write that value up above. And then let me use a different color. So 10. And then B represents, what does B represent? This value 11. And of course, we have 9 and 3. So A is in the extreme rightmost end, right? So A will be multiplied by the positional value 12 to the power 0. So I'm going to write here 12 to the power 0. Then B, the position of B has a value of 12 to the power 1. 9 has a value 12 squared. And 3 has a value 12 cube. And I'm going to put the values, calculated values of the exponents. 12 squared is 144. And then 1728 for. So I don't know why I keep writing 13. It should be a 12. 12 cube. All right. So we are multiplying each of these digits by their place value. So I put the multiplication signs. Yeah, we are multiplying, 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 and multiplying. All right, so starting from the rightmost end, 10 times 1, all right, so 10 times 1, 12 to the power 0 is a 1, 10 times 1 is a 10. So let me write that below here. 10 times 1 is a 10, correct? Then we do 11 times 12. All right, again, for this, you may want to use your calculators, but 11 times 12 has a value of 132. And then 9 times 144. 9 times 12 squared, which is 144, has a value of 1,296. And then we have 3 multiplied by 12 cube, or 12 to the power 3, is 1,728. So 3 times 1728 is 5184. All right. And then at the end, we add them all up, all these values up, and we get a value of 6,622. All right. So 39BA base 12 in decimal represents the number 6,622. All right. So again, as you see, the process is the same that you used when working with bases less than 10, except that the numerals are a little bit different. And of course, you have to use the positional values of base 12. All right. Now we will try to convert a base 16 number to base 10. All right. So the number in base 16 or hexadecimal is 7D and E. So remember, D and E here represents numbers. So let's look up the numerals for hexadecimal one more time. It starts from 0, goes all the way to 9, and then after 9, it's represented with letters of the alphabet starting from A being 10, B being 11, C 12, D 13, E 14, and F 15. So we have a D and a E in the number that we have to convert. So D would have a value of 13. All right, let me write that down. D would have a value of 13, and E would have a value of 14, and 7 is 7. All right. Also, we have to know the positional values, which will be based off 16. All right. So let me write that here. It will be the rightmost digit would be 16 to the power 0, which is a 1. Then 16 raised to the power 1, which is 16. And then 16 squared would be 256. All right, 256. And we don't have to go to the left of 16 squared because there are only 3 digits in the hexadecimal number that we are converting. All right. So again, same process, but I'm going to rewrite 7DE spaced out so I can show my work. So here we go. 7D and E, correct? And this is, you have to put that base 16 at the end. So E, let me write so I don't forget. E has a value of 14. D has a value of 13. And 7 is 7, all right? So the positional value of E is 16 to the power 0, correct? 16 to the power 0, which is 1. The positional value of D is 16 to the power 1, which is 16. And the positional value of 7 is 16 squared, which is 256. 256. So we have to do the multiplication here. So 7 multiplied by D multiplied by 16 and E multiplied by 1. That's how it's going to be. So let's do the multiplication now at the bottom here. So 14 multiplied by 1 is 14, correct? So I'm going to write 14. And then 13 multiplied by 16, 13 multiplied by 16 to the power 1, which is 16, has a value of 208. 208. And then finally 7 multiplied by 256 has a value of 1,792. And then we just add them all up for a value of 2014. 2014. So when the hexadecimal number 7DE is converted to decimal, it has a value of 2014. All right. So this is how we are going to work with bases greater than 10 for whether it's duodecimal or whether it's hexadecimal. All right, next we are going to do some conversions the other way around. That means convert a decimal value to base 12 or base 16. All right. Now we will perform a conversion from base 10 to base 12. All right. Now I've listed all the numerals for base 12 ahead of time here. Starts from 0, goes all the way to B. A is a 10, B is 11. And then over here, I have denoted all the positional values or the place values for base 12, starting from 12 to the power 0 on the extreme right-hand side. And then the exponents increase as we move to the left. And the calculated values are here, 112, 144, and 1,728. Now, when we are converting from base 10 to base 12, we use a process of division, correct? We take the number we want to convert and we first divide it by a place value which is closest to this number without going over. All right. So we are going to follow that same process that we used for converting with bases less than 10, from base 10 to bases that were less than 10. It's the same process that we are going to apply here, all right? So 6,652 is the number we have to convert. I'm going to write that down. 6,652, and I have to start by dividing it with one of the values which is closest to this number without going over. So 1,728 is the value, place value, which is closest to this number without going over, all right? You can try. I haven't written out the calculated value for 12 to the power 4. If you do the calculation, you'll see that it is a number larger than 6,652. So we'll start by dividing it with 1,728. So let's write that 1,728. So 3 times 1,728 is 4, 8, 1, and 5. All right. So 1,728 multiplied by 3 gives us 5,184. When you subtract that, you should get 8 and then 6, 4, 6 minus 5 is a 1. All right. So we take the quotient and we write it under the position, all right, under the positional value that we did the division by. So we should write it under 12 cube. So this is a 3, right? Let's write 3. Then we take the remainder, which is 1468. We have to continue the process of division, but this time we will divide the remainder by the next positional value, next lower positional value, that means. So we used 1,728. We have to divide it by 144. So let's do that. 144, and that would be 1 times 144 is 144. 6 minus 4 is 2. Bring down the 8. Now 28 is less than 144, so it goes 0 times. All right, so 144 goes 0 times into 28. So we are going to write 0 times 144 is 0, which gives us a remainder of 28. So here our quotient is 10. All right, so I'm going to write 10 below the positional value that we divided by, that we did the division with. Now we will work with 28, the next remainder, and we will, 28. So the next positional value is a 12, correct? So we'll divide it by 12. 2 times 12 is 24. Our remainder is 4, and our quotient is 2. So I'm going to write this 2 below the positional value of 12. So let's write 2. And then finally we have to divide 4 by the place value 1. Actually, if you can stop at this point and just put 4 over here, but just to be consistent with the process, I'm going to divide 4 by 1. That's the positional value of the extreme right hand digit. So 4 minus 0. So I'm going to write 4. All right. So now we are going to replace these numbers by the corresponding numerals of base 12. So 3 is a 3, which is fine. However, 10 is A, correct? So this is a 3. 10 is A. 2 is just 2, and 4 stays. All right, 4 is a numeral in base 12. So 6,652 converted to base 12 is 3A24, but you have to put a subscript here of base 12, indicating that this is a base 12 number. If you don't put it, even though there's A in it, people can mistake it thinking it's a hexadecimal. Hexadecimal also has an A in it, all right? So make sure that you specify by putting the subscript of the base this number belongs to, right? So next we will do a conversion from base 10 to base 16. Now this time I'm going to work through an example of converting from base 10 to a base 16 or hexadecimal number, all right? Now by this time you should all be familiar with the process of converting from decimal to a different base. We follow the same process of division, except that we are working with a different base and the numerals change slightly, all right? So I shouldn't have to explain every detail this time. You should be able to follow along as I work through this example. But for the first step, I will list all the numerals for base 16, all right? So it starts with 0 and goes along all the way to 1 less than 16, which would be 15, all right? So I have 8, 9, 10. Oh, sorry, no 10. It's 10 instead of 10, we have an A, B, C, D, E, F. All right? So that's 10, 11, 12, 13, 14, and 15. All right? Next, I'm going to list all the positional values. Well, not all, but as many as we will need to convert this number here that I have 9,455. So positional values from the right to the left would be 16 to the power 0, and I'm putting now the calculated value from the exponents. So 16 to the power 1 is 16, then we have 256, and then we have 4096. So 16 cube is 4096, all right? So we'll start the process of division. We will be dividing 9,455 by 4,096 to begin with. So 9,455 divided by 4096 goes 2 times 192. So the quotient after this division is a 2, and I'm going to write that 2. 2 below the positional value I divided by 4096. And now we proceed to dividing 1263, which is the remainder, by the next positional, lower positional value, which is 256, all right? So it's 4 for the quotient, and we have 1024, right? 464. All right, do the subtraction, and we end up with the remainder of 239. And I'm going to put the quotient below its positional value that we divided by, so 4. So now we continue dividing 239 by the next lower positional value, which is a 16. So 239 divided by 16. and we get a remainder of 15. So from this division, the quotient is 14, and I'm going to write 14 below the positional value. And then finally, we have to finish off with 15. So 15 has to be divided by the 1, the next lower positional value. So 1, 1. All right, and we get 15. So this has a positional value of 15. So now we have to put everything in the numerals for base 16. So we have here, and I'm going to use a different color. All right. So 2 is 2. So we keep that. Then 4 is also a numeral in the base 16. So 2, 4. But 14 is E, correct? This is the one. So we replace 14 with the E, and then 15 is replaced by F. All right. So 9,455 when converted to base 16 would be a value which is 2, 4, E, F, and don't forget to put the subscript of 16 to indicate that this is a base 16 hexadecimal number, hexadecimal value. All right.